Thanks. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. We just thank you, Lord, that you loved us even when we're not worthy of your love. Your righteousness is not based on our own, but that we can have your righteousness if we just accept your free gift, Lord. And we thank you for that. I just pray to be with us today. Help us to glorify you, what we do, and give us an understanding. In your name I pray, Lord Jesus. Amen. Okay, so I, let's see here, I told you guys last time that I would work this out at the start of class if you reminded me, which was a lie. I reminded myself, but I guess that's the kind of lie you don't mind. So to do that problem, we need partial fractions, right? And so, so I've started down the path. Actually, I did the partial fractions already on the board, right? N minus 2 factorial over n factorial simplifies to 1 over n times n minus 2, as we discussed last class. And so this came from number 38 and 9.1. This is not that problem, right? This is something I just invented as a side discussion, but it's a good problem, so let's work it. And I told you it was already clear. It's clear to me as soon as I get to the thing at the top of the board, which I'll circle in red. This expression right here, it's already clear to me that this is a convergent series, because it's clear to me from that I could compare it. I can do a limit comparison to p equals 2, and the comparison is going to be valid, right? And the fact that p equals 2 series is convergent means that that's also going to be convergent. So like that would give me an argument for convergence. But it wouldn't tell me what the sum of the series was, right? To actually find the sum, I can calculate the nth partial sum here using the fact that it's telescoping. I just have to look at the pattern, right? So let's work on that. See if we can't find. So this should also be, we could rewrite this as the limit, right? As n goes to infinity of the nth partial sum. The question is, what is that nth partial sum, right? So let's work that out. So we're looking, S sub n is going to invent a new letter, let's say k. K equals 2 to n, all right? 1 over k minus 1 minus 1 over k, right? And I just start working that out. See what that looks like. What does that give us? Let's see here. K equals 2. What do I get? 1 minus a half, right? What's k equals 3 give me? All right. And then a fourth gives me third minus a fourth, yeah? Let's try to write the last 3 terms just to be safe. Here's k equals to 2, here's k equals to 3, here's k equals to 4. I'm going to try to write down here k equals to n minus 2, just to be real thorough here. Probably don't need to go quite back that far, I think, from this pattern, but it's not a bad idea. So k equals n minus 2 means k minus 1 is what? N minus 3, right? And let's see here. K equals, then minus 1 over n minus 2, right? Plus then what? Plus k equals to what? K equals to n minus 1. Which gives me what? It gives me 1 over n minus 2 minus 1 over n minus 1. And then finally, k equals n. What's that give me? One over n minus 1. Yeah, minus 1 over n. This is, of course, telescoping, right? You're like, how did you know it was telescoping? I knew that it was telescoping when I saw the red formula last class, right? How did I see that?
split the red formula up into partial fractions.
Right, that is in fact how I saw it. And the reason I knew that that could happen was mostly experience, right? But so I don't think it's manifestly clear that that's a telescoping series just looking at it to start with, you know? I will admit there was some high-level insight going on there. So this right here cancels. This cancels with something we don't see, right? These cancel. This cancels with something we don't see. All we're left with is what? This guy and this guy. So the nth partial sum here is actually pretty easy to calculate. In fact, this Sn is actually what? We can replace this with 1 minus 1 over n, right? So in fact, the sum of the series is what? 1, right? Yeah, this series converges to 1. It's kind of weird, right? Like, what is this series? I mean, well, I started writing it, right? I don't like these ones, though. I'd really rather write it in its original red boxed form, you know? So it's 1 over, what is that? That's 2 times plus 1 over, what's n equals 3? It's 6, right? What's n equals 4? 4 times 3, right, which is 12. What's next? N equals 5, 20th. And then n equals 6 is 6 times 5 is a 30th, right? What is n equals 7? It's 1 over 42, right? And then n equals 8, I get 1 over 56. I mean, anyway, so forth and so on. That series sums to 1. It's kind of neat. I don't think that's at all obvious from looking at these numbers, is it? No. But this proves that that's the case. Carefully. Another thing I should mention, there's a proof question that I shied away from. And so the question basically was, you know, you've got this sequence r to the n, right? R to the n, where the absolute value of r is less than 1. Yeah. So my comment here would be that one way you could attack this would be to study the absolute value of r to the n, which would be equal to the absolute value of r to the n, right? And if I call this thing, let's say, a sub n, I think it's fairly clear that you can argue that that's a bounded sequence, right? This is bounded. 0 is less than, you know, this is less than, what's the upper bound? If this is true, what's this imply? This implies that the r squared is less than r, right? Which is less than 1, right? And you can keep doing this. The point is 1 is an upper bound to the nth term in this sequence. So it's bounded. You know? In fact, 2, if you continue in this way of thinking, you can see that r to the n, right, is less than the absolute value of r to the n minus 1, which is less than less than, well, I got the top of this chain up there, don't I? Which is a, you know, really sort of, what's the word? Clumsy way of me saying that it's, what kind of sequence is it? Is it decreasing? Is it increasing? the next one I didn't write. An plus 1 is what? Is it? It's less than a sub n, right? For each n. That's a decreasing sequence, which means like, so Nathaniel's like, wait a minute, so that's a bounded monotonic sequence. Therefore, by the bounded monotonic sequence theorem, it converges. In fact, if we study the other calculus book, which has math in it, it proves that it converges to the greatest lower bound. The greatest lower bound of this sequence is what? It's 0. So that's another way you could do the proof to that homework question. I don't think that's what your book intends. And if you want to see the epsilons and the, we come up with an epsilon m argument, Nathaniel? When,
yes.
Yeah, it took me a while, and I'd rather not go through it again. If you want to see the epsilon style argument, if you pay Nathaniel $1 or something, maybe he'll let you see it. I don't know. But anyway, so then the conclusion would be thus: r to the n is bounded monotonic sequence decreasing. Thus, the limit as n goes to infinity of the absolute value r to the n is equal to the greatest lower bound of the sequence. This is the greatest lower bound, which happens to be 0 here. Now, that's not actually even the question which is asked, is it, though, right? What did I just do? I mean, this argument shows that what I've argued at the moment is that the limit of the absolute value of the sequence goes to 0. But we have another theorem, remember, which says that if the absolute value of a sequence goes to 0, then the sequence goes to 0 as well, right? So this implies by yet another theorem that the limit of just r to the n as n goes to infinity is equal to 0. But that's by the connection between the absolute value of a sequence and just the sort of naked sequence. That doesn't work for any limiting value. That's special to 0. If I get the limit of the absolute value of the sequence converges to 3, I don't get to say anything about the limit of the sequence. You know what I'm talking about? Like, I could have this sequence. 3, minus 3, 3, minus 3, and so forth, right? This guy, I call this an, of course, an does not go to anything, right? It does not go to 3 as n goes to infinity, right? This sequence oscillates. It doesn't converge to anything, and yet the absolute value of a sub n is what? It's just 3, which is a constant sequence, which of course converges to 3 as n goes to infinity. The difference between that and what we just did is that 0 was the limiting value. 0 is special in this regard. So if you got some kind of annoying sign factor stuff going on in your expression, it's often a nice move to take the absolute value of it to get rid of that if you're trying to show it's 0. Standard operating procedure in calculus 2. Anyway, I have spent entirely too much time talking about this homework problem. I should open the floor for your questions. Dare I say comments? No, just questions. Just questions. Although Darius is not here, so I could open the floor for comments. It's somewhat safe. Since Darius is not here, let's talk about him. What do you guys think about that guy? I heard he skipped class today for some reason. He said he just wanted to improve his day or something, is what I heard. I heard there's a story that once upon a time such a student was a math major, and a math major who skips math class. This is a strange event. It's an interesting event, an event worth talking about. Perhaps this talk will have an effect on those not here. I don't know, but I should shut up. Anyway, you guys have. Can I erase this? Yeah. Okay. So which one do you guys want to ask me about? Remember the rules, chapter 9, preferably beyond 9.1. But if you ask me nicely, I'll do 9.1 as long as it's not past number 70. I think that should be a general rule. I won't take questions past number 70 today. You must ask me about questions before number 70 in any section. Whatever happens after that number seems bad for me to talk about.
Number 9.4, sorry, 9.4, number 6.
Number 6, that sounds like an ever so pleasant question. So this is, I like that. That's the kind of question we can talk about. And I might actually be able to offer you something in the way of understanding here. So we got 4 to the n. I trust your ability to transcribe problems more than myself at the moment. Plus 3. All right. So what is this like? What is this series like? My infinities are degenerating. What happens when n is huge? What's 3 as compared to 5 to the n? Put n equals to 3. What happens if n equals 3? What do you got? Upstairs you got 64, downstairs you got 125. n equals to 4. The denominator is 625 plus 3, right? 5 to the n dwarfs 3 very, very fast. That 3 is relevant to the tail of the series, right? So after a long time, this is it's really just the geometric series with ratio 4/5. This is nothing more than 4 to the n over 5 to the n after a while. It's like that. So I could try for like a direct comparison. That might work here. Or I could try a limit comparison. Now, why would it be worth comparing to? Like this. You know how to do this one?
No.
Okay, let's talk about that.
Yeah, let's talk about that, please.
That one's this we got to learn. So this one here, and it's part of your job in this chapter is pattern recognition. So when you see something that looks like n equals 0 to infinity of AR to the n, you got to recognize, oh, that's a geometric series. It converges to a over 1 minus r, provided what? Is less than 1, right? In fact, that thing I was just quibbling over is the bedrock for the geometric series. The fact that the absolute value of r goes to 0 if it's less than 1. That proof thing we were just talking about. The reason I assigned it is it's kind of important to the underlying logic of this central example for us. It wasn't just that I'm mean, although there's that. But let's see here. Let's not underestimate the meanness of Cook. Let's see here. Yes, thank you. So 1 over 1 minus 4/5. Yeah. So you're like, you see that r is equal to 4/5, and you also see that a is equal to 1, and it's geometric. So the way I would usually, in a solution, I would have a comment on the side, geometric, a equals blah, r equals blah, You say that, then I know what you're thinking, right? If the expression is more complicated and you just jump straight to this formula, I sometimes can't follow your work, and I might just think you're crazy. Not you specifically, but just generally speaking, Yeah.
So since that conversion, you can just say by DCT.
Oh, I don't know yet. I'm not there yet, but that's where we're going, I think. Let's get to it. So that what is that? That actually is. What is? Yeah, that's 5. Yeah. So I'll squeeze it in up here. This is 5. So in fact, this geometric series converges to 5. Then can we do direct comparison? If we take 4 to the n, what would we need if this is convergent, right? So to use direct comparison, what do we need? We need that to be.
I thought you need something bigger, right?
Oh yeah. So is this less than? Certainly 0 is down here, right? Definitely positive. Yeah, I think direct comparison will do it for us because 4 to the n over 5 to the n is clearly, like this denominator is larger than that one, so this inequality is legit. So yeah, thus by the direct comparison test, we find S converges. And I'm labeling this as S because it gives me no joy to write it again. I want to be precise, but I also want to save myself writing. Yeah.
So with the geometric series test, before I tried to use it on a problem, and I thought it made the problem like nasty. Let me see.
Are you asking me to do a nasty geometric series question? I mean, I can conjure one up.
Maybe not.
Yeah.
I thought so if it had equal to 0, it would diverge.
Equal to 0.
If the solution you got instead of being 5 had it been 0,
Had it.
that would diverge.
Now, what do you mean had it been 0? I don't quite follow you. If the denominator were 0?
No, like you know how like you got 5, like 1 over 1 minus 4 for the
Yeah.
now it's 0, that means it diverges? Or
Ooh, you're asking, could a geometric series converge to 0?
converge means, okay.
I mean,
I was thinking like backwards, I guess, because I was thinking like diverge, like,
well, I mean, both.
yeah.
You pick either one of these. If we just look at the nth term, it goes to 0. Okay. Yes, sir.
Sorry, I don't mean to hog the floor here, but it was 50.
I'm interested in any easy problems that I can solve with a minimum mental effort.
It was 9.2, number 64. Right. And I used
Ah,
A.
you are correct. This is a great example. This is the sort of thing I was trying to think how to make up. The fact that you've provided me an example just to work, perfect. So this is great. Your intuition that this was geometric series is correct. Now, perhaps that has come because this is from the geometric series section, and I can respect that. But also, yes, it is in fact geometric. Now, how can you tell it's geometric?
It's in the form there in power.
Yeah, right. It's in the right format. If that's not immediately clear, if you take an arbitrary term and take the ratio of two successive terms, you can detect that it's geometric. Anyway, so getting to the point here, this is just straight up geometric. And so this is going to be equal to a over 1 minus r, right?
5 over 1 that R.
1 minus, 1/3 x minus 2, yeah. So this is provided what? Yeah. So we need that x minus 2 over 3 is less than 1 for that to be the case.
Does it have to be greater than 0 or just less than 1?
It could be equal. 0, if that were 2, if we had x equals to 2, this would just be the 0 series, which converges to 0. There's no harm in that.
But like, does our R value have to be between 1 and 0 or just less than 1?
What I'm saying is if x equals to 2, that makes the r 0, right? I mean, x equals to 2 is r equals to 0 is what I'm trying to get at. R equals to 1 is the problem. And you can see that also in this formula. R equals to 1, oh no. That's, but r greater than 1 is also problematic because if we go back to the derivation of the geometric series, that makes the nth partial sum diverge. So only in the case that the absolute value of the radius is, the ratio is less than 1, do we get convergence to the geometric series. Now that here, we could also understand is actually the absolute value of x minus 2 less than 3, right? So this formula, which I'll multiply by 3 on both top and bottom to make it prettier, so let me make that 5 minus x downstairs. So this formula, this is good for what? The absolute value of x minus 2 less than 3, what is that? That's for x, an element of what interval? Its center is 2. See, if you look at this on the number line, that's saying the distance between x and 2 is less than 3 units. So it's 2 plus 3, 2 minus 3. That's what that is as an interval of numbers. 2 minus 3 is minus 1. 2 plus 3 is 5. So x in that open interval, we have this result. We don't usually have a variable in our problem, so this one's kind of an oddball, right? Mostly there's not this x floating around, is there? So this one's actually not one series, it's a whole family of series, one for each different choice of x. And if x is outside that interval, right? If x is equal to minus 1 or 5 or anything beyond those on the number line to the right or to the left, then this series diverges by the nth term test. Yeah? If you have the absolute value of x minus 2 over 3 is greater than or equal to 1, then S diverges. I don't know what the problem statement was, but here's a comment for you. So convergent is what I studied first, but I mean, x is a variable. I should address all cases in principle. Again, I haven't read the problem statement, so I may be going beyond what the problem actually asked for. Yep.
So it wanted us to find all values of x for which the series was converging, and then find the sum for those values. So then you would
Yeah, we did that.
you
Yeah.
plug in 0, 1, 2, 3, and 4.
Well,
Everything between negative.
oh no, x is a continuous variable here. So the answer is this right here, 15 over 5 minus x is the formula. That's what it sums to. And that's good for any x between minus 1 and 5, non-inclusive. Like this, I can, of course, rewrite as minus 1 less than x less than 5 if you like that way of thinking better. But
I'm just wondering, like, do we not have to find the sums for each of those x values?
I have. The sum for each x value is this. This is the sum for each such x value, right there. You don't want to list all the answers from minus 1 to 5. There are infinitely many real numbers. So you'd have like minus 0.5, then minus 0.499, minus 0.48. Okay, I'm going to stop making this point. There's a lot of numbers, but we are conditioned to think whole numbers are important, but in this context, not so much. So it makes sense what you're saying, though. I see why you'd say that, given our general discussion here and lack of thinking of a continuous variable inside the series. That makes sense what you're saying. I see why you'd be tempted to think that. This is really a foreshadowing example. This is more what we're doing after test. This is a power series, honestly. Power series centered at 2 that represents the function which I boxed as the sum. I'm getting ahead of the story. Okay, yeah.
So I worked it out like this, and the only reason I did that was because I saw it as an example.
Yeah.
Is there any truth to that? Or is that like incorrect at all? I mean, is
Well,
that incorrect? Like,
it's not incorrect. I mean, I don't think. So you're like an is equal to 5 times x minus 2 over 3 to the n, right? So if you calculate a to the n plus 1 over a to the n, you've got 5 times x minus 2 over 3 to the n plus 1 divided by 5 over x minus 2 divided by 3 to the n, right? And then you cancel the 5s, and you're left with x minus 2 over 3, right? I don't really need the parentheses here, do I? And of course, for x fixed, that's a constant, you know? You don't need to do that for this problem, though, because by inspection, this is that pattern recognizing thing I was saying. If you just look at this, you can see that that's a r to the n. Here's one where your idea would actually be like kind of maybe mission critical. Something like n equals 0 to infinity of, I don't know, 2 to the n 7 to the 3n minus 2 divided by 100 to the n. Oh, and oh, no, that'll do it. So like, that is in fact a geometric series, but I can't tell you what the radius is right off. So there are two ways you can find it. The one way you could find the radius is just by carefully looking at the first two terms and just seeing what it is, you know. So like this one, if I look at it, the first, put n equals 0, what do I get? Looks like I got 7 to the minus 2, right? Put n equals to 1, what do I get? Yeah, 2 times 7, I'm going to write that as 7 to the third power divided by 100, right? Times what? Times 7 to the minus 2, right? Now, if you knew for sure that this was geometric, that's enough. You can already tell from that what it is, because this, you could think of this as being the A, and this as being, well, in this, I've written it as RA, haven't I? You know? But the danger in thinking this way is you're kind of assuming the point, right? What if you did this procedure for something that wasn't geometric? You could deceive yourself into thinking it was geometric when it wasn't, right? Like if I go through the same thought process, so what I'm saying from this is it's clear to me that R is equal to 2 times 7 cubed divided by 100, right? What if I went through the same thought process for something like some, you know, n equals 1 to infinity of 2 to the n times n squared over 3 to the n. I'm like, aha, so this is n equals 1. I've got, you know, 2/3. And then n equals 2. I've got, what do I got? I've got 4 times, well, 4 over, what, 9? So if I think of this as being A, and this is thinking being AR, then AR over A is equal to, what is it? 16, well, I can't do math. Let's see here. Fine, 16 over 9 divided by 2 over 3, which is what? It's 8 over 3, right? So this series is geometric with radius equal to 8/3. Just one problem. It's not. It's not a geometric series. Just because I write the first two terms and pretend like that's R, quote unquote, doesn't make it such, you know? So to be careful, what you should do, if you don't recognize the pattern, is you should look at an plus 1 over an and see what it works out to. If it works out to a constant independent of n, then it's geometric. And if it doesn't, it's not. Over here, an plus 1 over an is what? It's 2 to the n plus 1, n plus 1 squared over 3 to the n plus 1 times, you know, 2 to the n times n squared, multiplied by the reciprocal, 3 to the n up here, right? And if you clean stuff up here, you're left with a 2/3, what? N plus 1 over n quantity squared. The ratio of successive terms here is not constant. It's not geometric, right? It looks kind of sort of geometric when you just glance at it, but it's not. This n squared is kind of your giveaway. That's not geometric. But this one, if you actually calculate an plus 1, which is 2 to the n plus 1, 7 to the 3 times n plus 1, minus 2 divided by 100 to the n plus 1, and I'll multiply by the reciprocal because that seems like a nice thing to do. 100 times n, 100 to the n rather, 2 to the n, 7 to the 3n minus 2. Be careful with your laws of exponents. And we get a what? We get a 2 left over we get a what? Times 7 to the, notice the 7 to the minus 2's cancel. That's the 149th, which is actually A. And you get what? 3n plus 1, so we get 7, looks like I get a 7 cubed. And downstairs I get 100, right? So that's the R. And it's geometric because R is independent of n. It's also divergent, right? Because what's 7 cubed? It's 49 times 7. It's definitely bigger than 100, right? It's fairly obvious that this is greater than 1, right? So therefore, S diverges. So I hope this helps, because I mean, I'm kind of responding to your question, Prince, which is more or less, how do I know if it's geometric or not, right? I mean, that's an important question that you must have a clear answer to in your mind. I don't actually, I'll be honest, like a lot of times when I work a problem, I don't actually go through all of this for a problem. I just kind of look at it and I see it as 1. And if it's not already 1, I will manipulate it until I make it such. See, because the other way to do this problem is just to take this expression and just to brute force rewrite it. It's 1 over 7 squared times 2 times 7 cubed over 100 to the power n. And if your algebra skill is sufficient, then this is not a troublesome step. You can do that. And that's fine. And you can identify from that A is 1 over 7 squared, and that the radius is what I just derived, which is 7 to the cube times 2 divided by 100. Right? So how do you want to do it? I mean, either way is fine, but I shut up. You guys have other questions? 9.4, number 20. I can try. This is, all of these numbers less than 70. Music to my ears. Let's see here. 9.4, number, what was it?
20.
Number 20. Limit comparison. Ooh. Ew. Ah.
Illustration of what we were just talking about.
Ew.
Yeah, you guys. You're the genius, my dude.
Not feeling good about this problem. Well, I got to make it. I don't know what to compare it to. Like just looking at it, like nothing jumps off. It jumps out. Would you? Anybody work this problem successfully? You can tell me what to compare to.
I compared it to 1 over 2 to the n minus 1.
You compared it to 1 over 2 to the n minus 1, which is what?
Which should be geometric because it's
Right.
times 1/2 to the n.
Okay, let's see if I buy into that. So you got the sum. Was it n over n plus 1 times 2 to the, what do you say? 2 to the n minus 1. And what's the n equals what to what? Okay. This is number 20 from section 9.4. Yeah. All right. So I think his idea is legitimate. I mean, for n really, really big, what's the major player in this series? If n is like 1,000,000, the n and the n plus 1, what are those? There's like 1,000,000 over 1,000,001. So it's essentially 1. So the dominant feature of this is this 1 over 2 to the 999,999 power. That's the main event here. The other thing is like 1, really, really close to 1. So this is pretty much dominated by the behavior of the 2 to the n minus 1. So that's why his comparison to, he says compare to this guy. Now, notice here, I'm going to be careful. This is a little bit different, isn't it? Can we two different ways we can go here. We can write there's a geometric series result. We could write starting the sum at 1, but you notice the one that I take as standard starts at 0. What does the formula look like if you started at 1? How is it different? let me do it a little bit different here. How about if we rewrite this as the summation of, let's say, k equals 0 to infinity, and what substitution would I make? How about k equals n minus 1? If I do that, then I've got 1 over 2 to the k. How about infinity? Does that change for the substituted variable? Like infinity is infinity minus 1. It doesn't change the upper limit, right? But the start of the series starts at 1 rather, as opposed to starting at 0. Now, if you actually work these out, it's the same thing, right? This is what? N equals 1 is what? 1 over 2 to the 0, right? Plus 1, 1/2. What's this? It's 1 over 2 to the 0 plus 1/2, right? These are just two different ways of capturing the same animal. But the right one is to be preferred at the moment because we already have a formula for the geometric series there. What is our formula if we start at 0? My point is you can recognize what is A and what's R there, right? Recognize what? Recognize. What's A equal to? A equals 1, right? R equals to 1/2. Yeah. I should actually take a, okay, so I'll get back to this issue momentarily, but anyway, the long story short, this series converges to what? One over 1/2, which is 2, right? Okay. So, I mean, Nathaniel's right. This is a geometric series. It's a convergent geometric series, right? And so we can do limit comparison test. Limit comparison test. Does the limit comparison test apply? Since n over n plus 1 times 2 to the n minus 1 is greater than 0, right? We can only apply limit comparison test to series with positive terms. This is such a series. So then we're supposed to do what? We're supposed to look at n over n plus 1 to the 2 to the n minus 1, and then divide by 1 over 2 to the n minus 1, right? What is that? Yeah, this is n over n plus 1, and what's the limit of that? Right, this goes to 1 as n goes to infinity, right? So thus, S converges by limit comparison test to sum equals n equals 1 to infinity. I should have given this a name. Oh well, it's too late. 2 to the n minus 1. Yeah.
Why can't you use the DCT instead?
The problem says to use limit comparison. Could we use DCT? Maybe. Maybe. Well, about the same, and we got to be careful, you know.
Can you do like blank instead of comparison?
I got to think about it. We need the right kind of inequality, right? We need this to be bounded below by 0, positive term, great. To use direct comparison, we need the geometric series is something larger which converges, right? Right? So is this, here's my question, is this less than 1 over 2 to the n minus 1? I mean, I don't know right offhand. I'd have to think about that. Is that true? I think you're right. I think you're right, because here's an in-between step. We can do n over n, right? That's legitimate, because what have I done? I've made over here you got a larger denominator, here you got a smaller denominator, then the n's cancel, and so, yeah, I think you're right. We could also do this problem by direct comparison. But, you know, limit comparison will still work for a similar problem. I can throw a monkey wrench in your plans real easy. All I do is I take this plus and I make it a minus, and then I got to be careful to start this thing at like n equals to, you know, 2 or whatever. And then I can't do direct comparison
And also, why was R 1/2?
without working. What's that?
Why was R 1/2?
That's by just this right here. I mean, this is, it can also be written as sum k equals 0 to infinity, 1/2 to the k. So if you look at that, you can identify, you can see a is equal to 1 and r is equal to 1/2. Hey, let's just let's work out the geometric series starting at 1, just so we have it. Sometimes it's nice to start the geometric series at 1 rather than 0, so it's worthwhile for us to just spend a second to derive it. Let's do that. How would you, we know this is true, right? So if this is true, what happens if we, say, reindex that, say, sum k equals 1 to infinity? I make a substitution. I want k to be equals to 1 when n is equal to 0. What's my k going to be then? How about k equals n plus 1? Does that make sense? K equals n plus 1 resets the lower bound from 0 to 1. And then I just substitute. Infinity is still infinity. A is still a. So I've got a, r to the what? I got to trade out that n for k. N is equal to? It's equal to k minus 1. See? And there you have it. This is the geometric series formula starting at 1. A, r to the k minus 1. Again, still converges to a over 1 minus r for the f's value of r less than 1. The formulas I just boxed here, these are the same formula, just rewritten a little bit. I mean, they're just different packaging, but it's the same thing, you know? Do you see why I prefer the one that starts at 0? Like algebraically, it's just kind of easier to look at, you know? And so many power series that we'll look at for not too long from now naturally start at 0 because the 0th term is a constant term. So like power series naturally index from 0, starting at 0. So it's not a bad thing to study series that start at 0 when it comes to us. But we should also be comfortable with like reindexing a series to start wherever we want it to. This kind of substitution is one of the skills that you want to work on mastering. I don't know if I've assigned many problems in that vein yet, so it might not be appropriate to test yet. Are there problems like this in your homework where you're given formulas in terms of one index and then asked to restart the summation somewhere else? Not yet. Maybe that's in the sections we haven't gotten to yet. I feel like it's somewhere in your homework, but I may be remembering stuff after the test, so it's fine. We have quite enough on this test in terms of what? L'Hopital's, improper integrals, right? All of this convergence, divergence stuff. There's a lot there. That's enough for one test, I think. Other questions? I mean, of course, there's the looming question, which is where's Darius? We could always come back to that, but okay. Let's see here. I hope he's sick. No, wait a minute, I shouldn't. No, fine. Sorry. Which one? Do you have one, Josh? You looked like you had a question brewing. You can just ask, it's fine. We've done a good work today. We can afford to try to answer an inappropriate question at this point. We're fine. 9.2, number 98. Oh my goodness, what have I done? What have I opened myself up to? Number 98, that sounds scary. Oh, proof. Oh. Let's see here. Two infinite series such that AN converges and BN diverges prove that the series. Okay, so you got two series, one diverges, one converges. Why is there some divergent? Right? That's the question. I think I know how to do this one in a way that you guys will understand and it won't be that technical. This was number 97 from section 9.2. Oh. Oh, thank you. So here's the deal. Let's suppose that this, well, we don't really care about the lower bounds here. Suppose that this converges. Suppose that this series diverges. All right. Our goal is to show that the series AN plus BN, with typical term AN plus BN, is also divergent. Right? So let's see here. Could we use perhaps the nth term test? What does the nth term test tell us about the first series? Right? By the nth term test. If it's convergent, it must be that the nth term goes to 0. What does the nth term tell us? The nth term test tell us about the second series? Oh, it doesn't tell us anything, does it? I was about to say it says that the limit of b sub n is not equal to 0, but that ain't true. I'm sorry. My dream of a very, very short and easy proof is dead now.
Can't we use the definition of divergence?
Yeah, we need to actually. We actually get into the proof is going to be by the definition. So what's the definition of converges then? The Sn, right? I usually put an upper A on it, which is what? The sum k equals whatever is 1 to n of a sub k converges, right? Let's say to A. Thus, the nth partial sum for B, right? What does that do? It does not converge, right? It diverges. So as a sequence, it diverges, right? So if we look at the sum of AN plus BN, n equals 1 to infinity, this has the nth partial sum being what? It's the sum k equals 1 to n of a sub k plus b sub k, which by properties of finite sums is just equal to the nth partial sum of A plus the nth partial sum of B. It must be that the nth partial sum, just the Sn, has to diverge. All right? So it must be that we must have that Sn diverges as n goes to infinity. Let me show you why. Why? Why, you might ask, right? So I'm going to show you a proof technique which is called contradiction. So suppose it did converge. What would that say? Suppose otherwise. What's that mean? That is, suppose that Sn goes to whatever you want to call it. Let's say Pac-Man. Suppose it converges to Pac-Man, where Pac-Man's a real number, right? Then what do we have? We've got SNB. What's that equal to? Solve for SNB. What is it? It's equal to Sn minus SNA, right? What are we assuming then? So I've assumed that this Sn is convergent. We're given that the partial sum for A is convergent, right? The difference of convergent sequences is also convergent. So this would converge to, Pac-Man minus, I called it A, right? As n goes to infinity. What would that say? Thus, SNB is convergent. Therefore, the series formed with terms b sub n equals 1 to infinity, is convergent. I mean, pick your poison. You could stop at the first thing. I mean, already here, we can stop right here, because this is a contradiction. What does it contradict? Yeah, it contradicts this up here, which is by the definition of divergent series, that the nth partial sum diverges. So if we assume that Sn converges, we get a contradiction, which means it cannot converge, it must diverge. Every series either converges or diverges, provided it's a single series. It doesn't have an x in it, like a sneaky example earlier. That wasn't a single series. That was a family of series with a parameter x, picking out different members of the family. Yeah.
Had a sub n also diverged, isn't there a possibility that it could?
We assume at the start of the problem that the series formed with terms a sub n converges.
Well, if you assume that it diverged, well, let's say it's a different problem, right? You say that they both diverge. There's no possibility.
Oh, if they both diverge, then the sum.
Is there a possibility that it could diverge?
It is possible it could convert. Right. And the most famous, the easiest example of that is something like this, right? If you do this guy, and you do this guy, these are both divergent, but this guy is also known as this guy, which is, we can all calculate without a lot of theory. I mean, the zero series sums to 0. So you're right. Those two diverges, and yet the sum converges. Yeah. You can also have divergent plus divergent is divergent. I mean, divergent plus divergent is, it's indeterminate, right? Infinity plus infinity could work out to, they could cancel, because one of them could actually be minus infinity in our language. When they're both divergent, you got to be careful when you put them together. Yeah. But if one is convergent and one is divergent, then you know what happens. The sum is divergent. That's what this problem shows, actually. Yes, sir.
I wanted to see if I did this problem correctly. It was summation is n equals 1. It's this one.
The 0.3 and 0.8?
Yeah.